Hi there and welcome to this new video. In this video we continue the kernel dev series. In the second episode we will start to see some C code. It's going to be very simple, very minimal, but we will go from the assembly of RISC-V into the C layer. Now to do that, however, it is important to discuss a bunch of things that we will use in our C code. So to understand the C code, we first need to understand two different concepts, which is that of inline assembly and compiler extensions. Then we will see the new minimal kernel, the new linker script, and the camo command is going to be the same as the previous episode. Now I hope this video is interesting, I hope this series is interesting. If you like it, please leave some feedback, subscribe to the channel, share this series with like-minded people. Thank you very much. If you want to support my work, there's also a Patreon. And if you're interested in the security of web application and Linux systems, I have courses on Udemy. Thank you very much and enjoy the video. Now, let's first start by talking about inline assembly. Now, inline assembly is used to tell the compiler to generate specific assembly instructions. Now remember, our objective is to write a kernel, and we want to write a kernel using a high-level language, such as C. Now, the characteristic of the kernel, however, is that it interacts with lower components, with lower layers, right? Like firmware, hardware, and things of the sort. And to do that, it has to interact with the CPU. And to interact with the CPU, it has to write assembly. And we will use a compiler to go from C to the assembly required to interact with the CPU. But in this process of generating the assembly code, we want to have control. There will be special circumstances, special situations in our kernel in which we need to have full control over the assembly we are generating. And to aid in this, the developers of compilers have introduced things such as inline assembly, which is a way to break the abstraction layer between C and the underlying assembly. Basically, with inline assembly, you can talk directly to the compiler and you can tell him, look, I want you to generate exactly this assembly code, no more nor less, exactly these instructions. We can use it in C like as follows, asm, and then we put as a string the assembly instruction we are interested in. This of course is a trivial example. In a more complex example, which is this one with the add function, we will also deal with input, output, and clobbered registers. So what's the idea? Well, the idea is that we can consider asm, the assembly, as a box in which we have some input, we're going to have some output, and this computation inside this block is going to change the state of some registers, right? Now we need to tell the compiler all of this information. We need to tell what is the code that we want to execute, what are the inputs, what are the outputs, and what are the used registers, which technically speaking, they are called clobbered registers. And how do we do that? Well, consider this add function. Here we're taking two arguments, a and b. We are defining a local result variable, which we are returning it, and the actual logic that implements the plus, the add operation, is implemented through inline assembly. Now here we have the add L instruction and the move L instruction. Here we are referring to these percentages 2, 1, 0. Now they're referring to either outputs or inputs. With the percentage 0, we are referring to the output variable, to this one that we are writing into the result local variable. Then with the percentage 1 and 2 instead, we are referring to the input variables, which are put into some registers. Now inline assembly is very powerful in this sense. It really allows you to specify if you want to use a specific register or a general register. And for example, for both the output and the inputs here, we are using the key R, which means use any register that you want, any general purpose register. So the compiler still has some choice in this, but we are limiting the choice it has. We're just telling it, look, I want you to take the value of this variable and put into any general purpose registers, and do the same with B. And then I want you to take the result of this computation and move it to the variable result, right? So that's the idea. Now, CC instead is a register that could be potentially affected by the operation, because here we have another operation. If you are going overflow, like in an integer overflow situation, it would change the CC register, which contains certain computer CPU flags, basically. And so we need to say that potentially this register could change. And this information is critical for the compiler to know, because given that it's not the compiler who generated this piece of assembly code, but we have handcrafted it, the compiler needs to know what could happen in that particular computation so that it's gonna generate before and after meaningful assembly code, and it's not gonna break everything, basically. So we need to be clear with that. Now, how do we work with this? Well, let's say that here we have this ASMA code. We can just compile it as follows, and we can just execute it. And notice, look at this, we get our result, 10 plus 20 equal 30. Now here, I can even compile with the bug symbols here, and we can, actually it's double G, and we can debug it with GDB, and here I can say this as add, and here we have the disas code of the assembly. Now the add and move here were generated because we told the compiler to generate exactly those instructions. Now if here I put, for example, an op, let me put it into the actual code here. Here I put an op which does nothing, by the way, so it's completely useless, and then I compile again. Actually, here I have to say semicolon at the end. I have to say semicolon, and then I compile at the end, and then I do this as add. Look at this, it has added an op, even though it's completely useless. Now, to make sure that the compiler will not optimize the code, we also need to use the volatile keyword, which tells the compiler, look, don't really do that, just put whatever I want in there, right? That's the idea. So in this case, we are pretty much loading the two local variables into the two register EAX and EDX. We are performing the add operation, and then we are moving the result into the EAX, which is then moved into the result local variable. So assembly inline is a powerful way in which we can work together with the compiler to produce the desired assembly code. And that was the first big idea that I wanted to come across in this second episode. Now, the second big idea for this episode are compiler extensions. Now, this goes along with the first idea. So we want to work along with the compiler. We want to work together to produce a desired output. Now, compiler extensions do exactly that. They tell the compiler to behave in specific way when generating code for a variable, for a function, for a piece of code, so they give us more control over the compilation process. Now, extensions are powerful concepts, but of course, when you have something powerful, typically you lose with respect to cross-compatibility. So maybe you have it in certain compilers, in certain systems like in Linux, but maybe you don't have the same extensions in other systems such as Windows or macOS. So be careful when you use extensions, only use them when you strictly need them, because they sort of like make the C code not really cross-platform. And one of the beautiful things about C is that it is actually cross-platform, right? So here I wanted to show two specific extensions, the naked extension and the section extension. Now the naked extension, actually it's not here, but it's here. So the naked extension will tell the compiler to not generate the so-called function prologue and epilogue. Now, what is a function prologue and epilogue? I've made a bunch of videos where I analyze the stack frame and the prologue and epilogue, so I'm gonna link them in the description. You can check out, I believe they are in the binary exploitation playlist also, so go and check that out. But basically, every time you compile a function, there is a piece of code at the start of the function and at the end of the function that is typically always the same, and it is used to set up certain state. For example, the stack frame to hold the local variables of your function. Now, sometimes we don't want that, and so to avoid having that, we can tell the compiler, look, do not put prologue and epilogue. For example, consider this. Here we are defining a my_naked function without prologue and epilogue. Now, if you don't have prologue and epilogue, you have to be careful though, because you cannot use local variable as always. You are pretty much losing the stack, the local stack. You have it to recreate on your own, so you're losing that, so be careful. But in this case, basically what we're doing is we're moving the value 42 into the output register and then we're returning it. So that's basically the idea. And then in the main function, what we do is we call the myNaked function through an ASM block, through inline assembly. So this is why we introduce inline assembly before talking about the naked attribute, because when you use the naked attribute, you should always use assembly to handle the logic and to make the call. And here I have this other example, it's called naked.c. It's called naked.c, it's the one that I've showed. And we can compile this, right? As always, simple C file, we can compile it, we can execute it. And we get a result from naked function 42. So we got the result there. Now look at what happens when we comment this. And here, let's say that we initialize this with 0, whatever. And then we are, like for example, if I don't initialize this and then I just say call my function like this, the code is not going to work anymore, of course, because now it's not really writing the result of this naked function into the result here. But if we go into something like this, also it doesn't work, because here I have to say result equal, sorry. Also this thing doesn't work. Actually, we have to compile it again. It says invalid usage of void expression. Now, if here I put int here, and then I do this, and then I compile it again, and then I execute it. Now, in this case, it does work, but I think it's not always the case. I think there's something that you should be careful. I cannot guarantee for certain, but be careful when you use the naked attribute, because the lack of the stack frame could create some problem. In this case, probably it's gonna be fine because we correctly write into the EAX register, so like we could use it like that, theoretically speaking, but in general it's dangerous and you should, because the compiler could add things that break everything, basically, so you want to be careful with that. And that is the first attribute, the naked attribute to remove the prologue and epilogue. Oh, and one thing which I forgot actually to do is, let's actually see what happens in terms of assembly code. I do naked, actually here I have to do gdb q naked like this, and then here I say this as my naked function, and look at this here, we don't have prologue and epilogue, we just have a move of 42 and then a ret, then an op, and then a ud2. Now if instead I remove the naked attribute here, let's say that I remove this, right? And then here I'm just gonna compile it again. I'm gonna do naked c naked, and then I'm gonna do gdb q naked, like this. Now I do this as my naked function, and look at this. Now I have both. I have the old instruction because they were put with inline assembly, but I also have the prologue, which is this thing, and the epilogue, which is this other thing. So something changed, right? With the naked, I don't have those. That's basically the idea, and that's why we use the naked extension. So that's number one. Number two instead is the section extension. Now, what does it do? It is used to place data or functions, so variables or functions, into specific places into the final binary. So I've made a video on C compilation in which you go from the source code to the object file into the final ELF binary, right? Now in this case, this attribute section is used to place into the object file the variable in a specific section. And then through the linker, this section can end up in the final binary, in the final ELF binary. So this is another example. Let's consider this code. Here we have a variable with custom data with the value 1237, and then here we have a function with the section custom text. So the variable will go into the custom data section, the code into the custom text section. If we execute this with a simple GCC, then we can use readelf to analyze the ELF binary structure and to extract, for example, the fact that we have custom text and custom data that were introduced by us with the extension, and the relative addresses, the base addresses before they are loaded into the actual process. So basically that's really useful if you want to place, okay, I want to lay out a binary with specific sections, and then I can refer to them, I can jump to them, you can use the extension section attribute, right? So that's the idea. Now, with having said that, we can now go and look at the actual kernel, because the new kernel itself is actually pretty minimal. So what do we have here? Here we have a bunch of type defs. Here we have some external, which we will discuss. Then we have the main loop of the kernel main, which is an infinite loop, it does nothing. And then we have the boot function. And as you can see here in the boot function, we are using the section extension, the naked extension, and the inline assembly. So to understand this, we needed to understand inline assembly, the compiler extensions, and we put it all together into this final code. So at this point, we will have a C kernel that we can expand and expand later on. So let's understand it bit by bit. We start with some type defs. So these type defs are used to, instead of having to write unsigned char, I can just write uint8_t. And to be honest, we can even make it shorter, and we can make u8 following the Rust convention. So u8, u32, and then here we have u32, usize. Now typically usize refers to the entire memory addressable. For example, if I'm working on a 32-bit, I need to use 32-bit to address the entire memory, so usize is gonna be 4 byte, 32 bits. If instead I'm on a 64-bit system, then basically I need 64-bit to address the entire memory, so usize is gonna be 8 byte. So that's the idea. So this is just for convenience, these type defs. Now here we find an interesting bit, the external char. So these are addresses basically. They represent pointers to the memory. Now these pointers are actually initialized, they are set by the linker during the compilation process. So during compilation, the linker comes up, it understands the final addresses for this variable, and it hooks them up into these variables. Which means that in the C code, when we use this variable, for example, look at this stack top, here we're actually using these variables, and these variables are going to be initialized by the linker. So the linker is going to tell the kernel what to do, basically, the value of these variables. Here we have a kernel main void with an infinite loop, nothing to say here, and then here we have the boot function. Now the boot function is going to be naked, so no prologue and no epilogue. It's going to be put in a specific section called .text.boot, and it's going to have this code with asm volatile, so inline assembly that is not optimized by the compiler. So we're going to move the variable stack top into the SP register, which is the stack pointer, so it is the register used by RISC-V architecture to handle the stack. And then we're going to jump to kernel main. That's it, we don't do anything else. We just move the pointer and we jump to kernel main. And here we have no output of the process because it's going to go into an infinite loop. And the only variable that we pass is the stack top variable. We use any register and we're going to refer to it within this assembly piece of code with the stack top label. So basically that is the idea. The effect of this is going to be, it's going to initialize the variables, it's going to go to kernel main, and it's going to have an infinite loop right there. So that's the idea. Now remember in this case that the stack will actually grow downwards. So here is going to be the SP into a high address, high here. Here up are going to be the low addresses, and so we're going to grow back, we're going to grow downwards. So we're going to grow towards lower addresses, and so the kernel has access to this at this point, right? Because we have the variables. Now to compile this, however, there's one last step missing, right? Which is the linker. So here there's the description of what I've just said. And finally, we need just to analyze the last piece of the puzzle, which is the linker script. So the previous linker script was simple. Now it's going to get a little bit more complex, but we will read it step by step. Now the objective of the linker script is to tell is to declare how the binary should be structured, right? It is ultimately to construct the final F binary. So to construct the final F binary, I start with all the object files and I put them together, and I use this linker and this linker script to tell the linker, okay, you have to assemble the pieces exactly in this order. And so what do we tell the linker? We tell that the entry point is the function boot, so that's number one. We tell that we have different sections. This section starts from the base address 802.0.0.0.0.0, and this is after the OpenSBI layer, right? So first we have OpenSBI, and then we have our custom kernel code. Then we have the text section, which contains the actual kernel instruction. So we have first the .text.boot, and we want to keep this symbol. So we want to keep this symbol into the final F binary. And then we have all the other text, section of text, basically. Then we find the read-only data. Now the read-only data, as you can see here, it is aligned to a 4-byte boundary. So this tells the linker that at this point the linker has created this elf, here this base address, and then here it has put all the text. At this point it's gonna have some address. It's gonna reach a certain address. Now when we say align 4, we are telling the linker, look, the starting address of read-only data has to be aligned to a 4-byte boundary. For example, in hexadecimal, it means that the last byte of our address can either be 0, 4, 8, 12. I mean, 12 in hexadecimal would be A is 10, B is 11, C is 12, so C, or F, which is 16, basically. No, because F is 15. So like we have this or 16, or we go back to 0. So 0, 4, 8, C, 0. Basically, that's the idea. So we want to say we want to be aligned to this kind of boundary memory, and it is important for the processor to work smoothly. Like sometimes alignment is important. Then we put all the read-only section, then we put all the data section, and then we put the BSS section. And look at this, in this BSS, we are defining this variable underscore BSS equal dot. So basically what we're doing is we are taking the current address and we are assigning it to the variable BSS. This variable is the one that was accessed by C using the external char syntax. We do this for BSS, and we also do this for BSS end. So we are taking these two symbols, and of course, between the end and the start, we put all the sections related to BSS. So we put all of those. By the way, here there was a glitch where there was a comma here. That was something with Emacs, so there shouldn't be no comma there. There should just be asterisk, basically. So we just have asterisk here. So basically we have the data, we have the BSS, and finally we have the stack. We want the stack to be aligned to a 4-byte boundary, and we want the size of the stack to be 128 kilobytes. And so we add this amount to the address to get the stack top, which signals the end of the stack. So basically we're gonna have the stack, which is gonna be from stack top to the start, and this is gonna be 128 kilobytes. And of course, we can increase it, we can decrease it. For now, it is statically defined in this linker script. So that's the idea. Now, when we want to compile this, what we're gonna do is we're gonna use this command. So we're gonna use the GCC toolchain with respect to RISC-V, and I've showed in the previous video how you can download this toolchain. We're gonna put the -t to put the kernel linker script, the linker script for the kernel. We're gonna put no stdlib to say I don't want to be linked with the standard C library. Because remember, at this point we are compiling C code. Now typically C code is linked with the standard C library, which assumes the presence of an already existing operating system, but in our context we want to create a new operating system, therefore we don't have that available, so we cannot link with the standard C library. In the future we will have to implement our own standard C library. Then I have the -O2 for the optimization flag, then we have the -G3 for the debug, then I have for the error, WAll and WExtra. Here I remove the canary protection, the fno stack protector. Here I say freestanding means that the binary is going to be executed in an environment without operating system. So this is used, for example, if you have to do embedded development, because in an embedded device you don't have an operating system, maybe you have to write your own operating system. Then here we are telling the compiler to print out a kernel.map, which contains the mapping the various sections of the binary. So this is going to be produced as output. We put the kernel.c file, the input C file, and then we put the -o, the kernel.elf, the output file. So here we're gonna put here, notice that I don't put the double dots because in this case the toolchain is in the current directory, so I'm fine with that. So here I have the toolchain here xpack, so I'm gonna use this. And now I have this kernel.elf, perfect. I can say file kernel.elf, It's a statically linked executable for RISC-V. Now, how do I get the QEMU execution? Well, it is the same command as before. Nothing changes. The only thing is that now it is not print.elf anymore. It is kernel.elf. And so we do kernel QEMU like this. And here, boom, we are executing our kernel. Of course, you don't see anything. Why? Because our kernel does nothing. It enters into an infinite loop. We see the typical OpenSBI output with all the platform thingy, the file that we are virtualizing, perfect. Now, if we want to make sure we've done everything correctly, there are a few things that we can check. We can go into the QEMU debug console by pressing Ctrl A and then C. Here I have the QEMU debug console. At this point here I can write info registers to get hold of the register's value. And of the register I'm interested in two specific registers. I'm interested in the program counter PC with this value of 8020000E, and then I'm interested into the stack pointer, these two, x2/sp, with this value 802.20010. Now, how can I use these values to make sure that everything is gone well? Well, what I can do is I can first of all, here, I can check the info registers. I can use the objdump utility of the RISC-V toolchain to go and print out the code for the binary. And in this case, here I also have to say 1 dot, not 2 dots. And here I get the following situation. Now, as you can see here, we don't have much code because this is like a minimal kernel, but we do have kernel main. And kernel main, the instruction for kernel main is at this address, 802.0000E, which is exactly the one that was found in the program counter. And of course, this piece of code goes into an infinite loop because here we're just keep looping over the same address. We are just keep jumping over the same address. And as far as the program counter went, the program stack went, sorry. So the stack pointer, to make sure that the stack pointer is properly set, we can actually do it in two different ways. Either we cut the kernel map and we grab for the stack top variable. So the kernel map was generated by the kernel and we have the stack top variable at this particular address, which is the same as the one found in the QEMU execution, dynamic execution. Or we can also use the nm utility to print out the symbol. So we do this nm and we make sure that we have a match. So what we want to make sure is that we have a match between the QEMU environment that is dynamically executing and the symbols, the address for the stack top variable, and for the instruction that goes into the infinite loop, the kernel main function. And so basically this is it. Now we have this minimal kernel, and in the next episodes we will see how to expand this C code, how to add feature, how to implement a small C library in the kernel level, and how to add all the facilities that a typical operating system has. I hope this series is fun, I hope it is enjoyable. I'm gonna put in the link the reference that I'm using for making this series, which is Operating System in 1000 Lines of Code, which I thank the author for having written and published it on the internet. Thank you very much, and thank you for watching the videos. If you're interested in more, by the way, let me know because it's gonna encourage me to keep making videos on this series. So that's it, and to the next video.